All right, this is the first video in AP Calculus on anti-differentiation or integration by substitution. This is also known as U substitution, and that's what you're going to hear me refer to it as for the remainder of this section, or this unit, really, or the year. So we're going to begin with just some properties of integrals. We've been using a lot of these already as we've been doing them, so this really should not come as anything new to you, because the whole concept of an integral is that basically you're going backwards given a derivative. The first one, which we've talked about before, is doing a constant times a function. You can also just pull that constant out in front of the integral, integrate the function, then multiply by the constant. We have the addition and subtraction properties. You can split a complicated integral up into individual functions and add or subtract them. You cannot do that with multiplication and division, however. The power formulas, this is basically the reverse power rule here. I don't really ever give it to you in notation, but we kind of think through it. You know, add 1 to the exponent, and then for the coefficient, you do old coefficient divided by new exponent. The only power where that's not the case is when it's to the -1 power, because that's the same as saying 1 over u, which integrates back to the natural log of u. Then we have our trig integrals. Those are just the reverse of the derivatives. The derivative of sine is cosine, so the integral of cosine is sine, and so on and so forth. The integral of secant squared is tangent. The integral of secant tangent is secant, and then you've got the ones on the right as well. And then also with exponential and logarithmic functions. Remember that e to the u is its own derivative, so therefore it is its own integral. Natural log of u is a little bit different. That's not really something that we ever integrate in AB calculus. And in BC calculus, we will look at that more when we get to integration by parts in a few more sections. So don't really worry too much about it right now. Log base A of u, the formula is there, but again, that's not really something that we do in AB or in BC. And then the a to the u, that you could see in either course. Remember that a to the u is its own derivative, but then times the natural log of a. So if there's not natural log of a written over here in this integral, then that means we have to divide by it in the original. So all of this is just thinking backwards. So you really kind of have to remember your derivatives and their rules so that we can then apply them in reverse to integrals. So for example, if I have the integral of cosine of x minus 3x squared, I'm going to split this up into the integral of cosine x. Notice I'm putting a dx at the end of both of them because that tells us what variable we're integrating with respect to. So don't be sloppy and leave that off. All right, so we start with cosine of x. Well, cosine is the derivative of sine, so this is going to integrate back to sine of x. X squared, I can do reverse power rule on that. That would have come from x to the third. And then if I do old coefficient divided by new exponent, so that becomes 1x cubed. And then since this integral does not have boundaries on it, I have to remember to put the plus c at the end because it's an indefinite integral. So that whole integration process should not be anything new to you. This is something we've been doing for a while. It was included in the test in the last unit. You should be okay with that. Now we're going to look at what if it gets a little bit more involved. So here, for example, I want to do the integral of x cosine of 2x squared dx. Now I'm looking at this and I actually see multiple functions. I see x, I see cosine, I see 2x squared, and the 2x squared is actually inside of the cosine function. When you see a function inside of another function, well, if you think back to derivatives, functions inside of functions, that involved the chain rule. And remember the chain rule, we would do the derivative of, so if this was f of g of x, we would do the derivative of the outside with the inside left alone times the derivative of the inside. That was how the chain rule worked when we were taking derivatives. So what we're looking at here is we're actually looking at what we would have ended up with using the chain rule on a composition. So when you see a problem like this with a function inside of another function, you need to realize, oh, I'm going to have to reverse the chain rule here. And that can be kind of tricky to do. So the process we use to do that is U substitution. And they're actually kind of giving us a little bit of a leg up in this problem. they're saying make u be 2x squared. So that means that I want to replace this 2x squared with a u, which would make this cosine of u that I'm trying to integrate. Now the other stuff that's in here though is x and dx. Now I have a problem because I have the letter u and I have the letter x all inside the same integral. That can't work. I can't integrate it when it has mixed variables like that. So I need to somehow replace the x and the dx in terms of u, so this can be one simple integral in terms of u. So how we do that is, well, if we know that we're going to use u equals 2x squared, then that would make du the derivative of that. So the derivative of 2x squared would be 4x dx. Now, if you go look at my integral, I have an x and I have a dx. I have an x and I have a dx. The one thing I don't have is a 4. So the 4 needs to come over here. And so 1/4 du is equivalent to x times dx. So I can replace the x and the dx, even though they're not right next to each other, they're still all being multiplied there. So I can substitute 1/4 du for those things, and then the cosine of u I bring down from my earlier substitution. So now if I had put this red integral on your paper from the beginning and said integrate 1/4 cosine of u, well, you could pull the 1/4 out in front, and then you could just focus on integrating cosine of u. Well, cosine is the derivative of sine, so this would integrate back to 1/4 sine of u plus c. Now here's the one thing we have to remember to do. This problem was not in terms of u from the very beginning. It was in terms of x. So once you have integrated it all the way, you then have to go back and re-substitute in place of the u. So we have to put back in, instead of u, we have to put in that 2x squared that u is equivalent to. So your final answer for the integral of x cosine 2x squared dx is 1/4 sine of 2x squared plus c. All right, so let's look at another one here. They have told us what our u needs to be again. So again, they're kind of giving us a little bit of help there. So I can already tell that this is going to get replaced with u. So I need to figure out how I'm going to deal with the dx. So now that I know what u is, the very next thing I do is find du by taking the derivative of u equals 7x minus 2. So the derivative of 7x minus 2 is 7, but it was a derivative in terms of x. So I'm going to write dx next to it. So I don't have a 7 dx though over in my integral. I have a dx. So 1/7 du is equal to dx. So that makes my integral, the 28 is still there, but I would have a 1/7 du. And instead of 7x minus 2 quantity cubed, it's just going to be u cubed. Well, that becomes 28 times 1/7 is 4 u to the third du. So then it's a real simple reverse power rule. I add 1 to my exponent, and then do old coefficient divided by new exponent. And then don't forget your plus c. So that becomes a 1 u to the fourth plus c. But don't forget to go back and replace your u with 7x minus 2. So your final answer is 7x minus 2, quantity to the fourth, plus c. All right, so those two weren't too bad because I really kind of held your hand through them, and because the u was predetermined for us. Like, they told us what to use for our substitution. That's usually not going to happen. So let's look at some where that's not given to us right off the bat. For example, here I have the integral of x plus 2 to the 5th power. Now, I'll be honest, you could sit here and you could FOIL out x plus 2 times x plus 2 times x plus 2 times x plus 2 times x plus 2. FOIL all that out, combine like terms, and you could integrate piece by piece. That's really not what you want to do. And that's probably not how your answer choices would be written on a multiple choice question. What I notice here is that I have a function inside of that fifth exponent there. So the inside function is usually your u. So let's try it with u being x plus 2. If I then take the derivative of that, the derivative of x plus 2 is 1 dx. So this is a very simple and straightforward substitution. In place of the x plus 2, I put a u, and in place of the dx, I put a du. Now it's just reverse power rule. Add 1 to the exponent, old coefficient divided by new exponent, put the plus c on there. And then once you've worked through the integration process, be sure to go back and substitute that x plus 2 in for the u. And then don't forget your plus c on the end. That's how it works. Okay? All right, so we're going to do one more together. Actually, I want you to pause the video at this point and see if you can give this one a try on your own. All right, so hopefully you chose the same u that I did, 4x minus 1, since it was under that radical there. 4x minus 1 was your inside function, which made du 4 dx. Then you had to bring the 4 to the other side, so you had 1/4 du is dx. I replaced my 4x minus 1 and my dx in terms of u, changed my square root to a 1/2 power, and then I just did reverse power rule. If you're wondering at all where this 2/3 came from, I would have had 1/4 divided by 3/2 when you do old coefficient divided by new exponent. So keep change, flip that, you get 1/4 times 2/3. So that's where that came from. And then end result, 1/6 times 4x minus 1 to the 3/2 plus c. All right, so I want you to pause the video at this point and give the next two problems, C and D, a try on your own as well and see if you can get them. All right, so I ended up with 1/7 sine of 7x plus 5 plus c for the answer for C. I used 7x plus 5 as my u. So then 1/7 du was equivalent to dx, which made my integral 1/7 cosine u du. And we've already done a cosine integral today. That just worked back to 1/7 sine of u plus c. And then I went back and put the 7x plus 5 in for the u. Then for D, you had to kind of catch something in order to make it work for you. You do start with that innermost function. So 2x was your u, which makes 1/2 du equivalent to dx. So my integral became 1/2 times 1 over cosine squared u du. Here's the trick. You had to realize that 1 over cosine squared is the same as secant squared. Because then secant squared is the derivative of tangent. So that real quickly integrated back to 1/2 tangent u plus c, and then you replace the u with 2x. All right, so that's our introduction to u substitution. We're going to continue working on the remainder of the practice problems in the next video or the next time that I see you in class.